see. Ben is up first.
Ben is up first. He's right. He was just there. He is right there. Yeah. Are you just making it get ready for me?
What's that?
You just getting ready for me then?
Yeah, I was just getting ready for you.
Okay.
And maybe just mention this is part 2 now. We're going to get into understanding how how this is going to go into our practices. We're going to talk about next day.
Yeah. Okay. This next session is on pond hydrology and pollutants. The theme of this session essentially is melding together research and application. Those researchers at the University of Minnesota and others are helping to inform engineers on the ground and what they are doing. And then once engineers build things, how those come through and take those and modify them and use them as part of their practice. So our first presenter today, a series of 4 presenters. Our first presenter is Ben Janke. He's a research associate at the University of Minnesota, SAFL, and he'll be talking about pond hydrology, pollutant inputs, and internal dynamics. Welcome, Ben.
All right. Well, thanks, everyone, for being here. It's great that we actually, I don't have to run through the usual introduction and try to convince people to care about ponds, because that's the reason you're all here, so this is great. So in the next 20 minutes, I'm going to try to talk about everything we've learned about ponds in the last 10 years. So like I said, the motivation doesn't need a lot of introduction. A lot of what I'm going to talk about has to do with phosphorus, since that is sort of the nutrient of concern. There's a lot of permitting and rules related to that. So that's been a lot of the focus of the work. We know that a lot of the ponds in the Twin Cities have high phosphorus. But before I move on, I just want to point out that there are a lot of other things happening in these ponds that we're also interested in and have been studying to some degree. You know, ponds can be good for denitrification and removal. They can be sources of greenhouse gases, especially methane. They also accumulate heavy metals, microplastics, hydrocarbons, things like that. Leah Pollack, who has a poster here, and I think Christoph Zwiefel, if he's here, has one on lead. So if you're interested in some of these contaminants of emerging concern, check out those posters. And we also know that these ponds provide habitat for a lot of critters who are trying to make a go of it in a pretty challenging system. So one of the guiding questions, kind of from the very beginning of this research, is this idea of aging ponds. So as we've been using these for stormwater for decades, are they still providing a water quality benefit? Are they still providing phosphorus retention? Especially as they accumulate sediment, organic matter, phosphorus, there's dense vegetation growing in and on and around the ponds. Are they still functioning as we think they should? Some of the research goals over these many projects going back to 2016, really trying to identify the processes in ponds that affect phosphorus retention, trying to develop some indicators of poor water quality performance in ponds, and then trying to turn this into guidance for assessment and management. This has been the focus of work for the team listed here and a lot of other people. You'll hear from actually everyone in this list throughout the next 2 days. We've had a lot of funding from MSRC, Local Road Research Board, MSP LTER, and of course a lot of cities and agencies have also supported us. So phosphorus retention is it's a complex process in ponds. And when we talk about retention, we're kind of thinking about that fraction of inputs that's retained in the pond that doesn't become an output. So kind of a simple mass balance in versus out. But there's a lot of things happening in ponds. The watershed inputs are very intense, especially compared to maybe a lake, a larger water body. There's a lot of things happening around the pond. We have tree canopy that's sheltering from wind or providing direct nutrient inputs. There's a lot of plants growing around or in the ponds. Sediment characteristics are also really important. There's a lot of organic matter. And there's a lot of internal processes. Really, at the core of all of this is dissolved oxygen. That's kind of the glue holding this mess together. But a lot of these internal processes are either affecting DO or affected by dissolved oxygen. And one of the main concerns is this idea of internal loading, so this redox reaction that happens under low oxygen conditions releases soluble reactive phosphorus into the water column where it can be taken up by algae or duckweed. And so that's kind of the management concern kind of from back in the beginning. Our data collection design, we kind of threw the kitchen sink at it, basically. We included some sort of comprehensive surveys where we go out maybe once or twice a year collecting data in ponds or surveying ponds. This might emulate the sort of practices that practitioners might use if you have maybe dozens or hundreds of ponds to inspect. We also did some intensive kind of biweekly sample collection, profiling. We have roughly 50 sites now, probably in this data set. We did some continuous monitoring. This is more intense sort of work. This is largely what I've been responsible for better or worse. This is sort of continuous monitoring of like water level, temperature, DO, things like that, and also wind speed, which I'll talk about in a bit. We have lab studies of sediment cores. Purnima Natarajan at SAFL has led a lot of this work. She'll talk a bit about this later, but taking the sediment out of the pond, taking it back to the lab for study. And then we also leveraged the existing data sets that all of you wonderful people have collected over the years and trying to put that together into what's really now a pretty impressive database of pond data. So where we started out was with the initial project was really trying to understand what's coming into a pond, what's leaving, can we do a phosphorus budget for a few ponds? We were working in Roseville in this project, these 3 sites, maybe not the most diverse sites, but definitely different in terms of size and watershed area. We did year-round monitoring with ISCOs, compositing stormwater and snowmelt samples, and also pairing that with some grab samples and profiles in the ponds. We did this work from late 2016 through like fall of 2018 so that we could get at least 1 year of good data for each site. Very hard-won data set. So I'll just kind of go through some of these results and what we learned from that first project. So as you learned, this is the phosphorus loading for the Alameda pond, just as an example here. Those percentages you see there are the retention percentages. The first bar is TP, 53%. So that's pretty close to that 60% that Ross and others were talking about earlier. We can see that that retention is driven by a higher particulate phosphorus. That's the middle column there, particulate phosphorus retention in the ponds. For the other 2, the William Street Pond, 56%, and the Church Pond, our winner with 78% TP retention over the year. Interestingly, that's the only pond of the 3 that was a designed and constructed pond from the 90s. If we look at the concentration data, we get a little more information. This is just the first bar is the inlet TP, the second bar is the outlet TP, the shaded portion is the particulate. And what we see in the Alameda pond is that we have a reduction in phosphorus concentration from inlet to outlet, so that's kind of what we'd expect to see, but the proportion of phosphorus is kind of remaining the same there. If we look at the other sites, things are a little bit different. So the William Street Pond also had a reduction of phosphorus from inlet to outlet, but it's mostly driven by dissolved phosphorus reduction. And that's because this site has an iron-enhanced sand filter bench on the outlet. It's clearly working pretty well, at least it was in 2017. I assume it's still doing its job. The Church Pond, interestingly, had a higher phosphorus concentration in its outflow than the inflow. And yet it had the highest retention. So how does that happen? And that's basically because it was retaining most of the water that was flowing into it. It just didn't discharge very often. When it did, it was high phosphorus water, but it was holding on to most of the water or losing water. So that's why the water balance or hydrology of these ponds is really important. You can see it varies a lot across those 3 sites. And luckily, I don't have to explain the schematic because you've seen it 3 or 4 times already, but this idea that the ponds have a permanent pool, and really if there's no water loss in the pond at all, no evaporation, no exfiltration, they should have a pretty neutral water balance. They just fill up during an event, slowly discharge over time. What was happening in the case of the Church Pond especially is it had this surplus storage. The water draws down below that discharge elevation, maybe due to exfiltration, evaporation, and therefore it was able to retain a lot of the events that flowed into it. We can look at this at event scale. I'm sorry, you're going to see a lot of graphs, so I'm going to do my best to explain these, but this is now looking at total phosphorus retention at event scale. Each point is one event. The colors correspond to the different sites, but that isn't really important here. But what this diagram is showing is the points above the origin on the vertical axis are net total phosphorus retention. The points below that are net export for that event. So that would be the pond not doing its job. On this x-axis is just that surplus storage. So to the left of the origin, that's where there is surplus storage, the water level is below permanent pool. 0 just corresponds to the permanent pool elevation. Then to the right would be where there was still water in the pond when the event started. So maybe you have a sequence of events or rain on top of snowmelt, something like that. Kind of the take home here, though, is that if there is surplus storage of really any kind, you're going to achieve some kind of phosphorus retention. So this is really kind of an argument in favor of something like adaptive control, because even a few centimeters, a few inches of antecedent storage is helpful for improving retention. So that's kind of the take home there, but also that the water balance is really important for these ponds. So as I said, that was a lot of work. This is not really a feasible approach if you have lots of ponds. And there's a lot happening in the ponds that we really need to understand to better manage them and better understand how to improve retention. So the question kind of becomes, what have we learned then from this maybe simpler data collection in and around the ponds? What can we learn? So I'm going to give you the highlights right here and then kind of walk through the data. So one of the first things we found that was really kind of a surprise is that many of these ponds, even the shallow ones, were stratified and low oxygen. And that low oxygen tended to drive high phosphorus concentrations. You see a relationship there with lower oxygen, higher phosphorus. In the lab studies, we saw that there's high sediment P release potential under low oxygen conditions. So this does suggest that we have an internal loading problem in these systems. I'll show the evidence for that next. What was sort of our green elephant in the room that we just sort of ignored at first was all this floating vegetation, duckweed and wolfia. We just kind of ignored it first, but it turned out that in the ponds that had very dense duckweed cover, they were low oxygen, high phosphorus. So this has implications as an easy indicator, because you can just go out to a pond and see that it's covered in duckweed. So hold on to that idea for a talk later this afternoon. So here's kind of the evidence for what I just told you. So each of the points in this plot now is an individual site that we've monitored over time. And what this is showing is that as the mean water column average of DO increases in a pond, the phosphorus tends to be lower. So at low oxygen, we have quite variable, but tend to have higher phosphorus. In the lab studies of the sediment cores that were brought back to SAFL, we see high phosphorus release rates from the sediment under those low oxygen conditions. That's what this plot is showing us, the brown bars. There's a lot of variability across sites, and there's actually way more sites in this data set now that I'm showing here. This is just kind of a sample, but it's variable across sites, but most sites will have phosphorus release under low oxygen conditions. If we do our best to adjust this for the actual anoxia being observed in the field and plot that versus phosphorus, which is the total phosphorus in the water, we can see it's a rough relationship, but there's definitely higher phosphorus in the ponds that have higher release rates. And again, kind of suggesting that we have an internal loading problem, which the implications are, as Ross said, some of the more promising management strategies might be the sediment amendments with alum or iron. As I said, oxygen is really important for these systems. It's kind of, it's what's driving a lot of these patterns. So what is controlling DO in ponds? And aquatic vegetation is really important. Macrophytes, algae, photosynthesis tends to put oxygen into the water. But as I said earlier, duckweed, which is being shown in this plot here, tends to suppress oxygen in ponds, especially when it's present at very dense amounts, kind of on the right side of this graph. You have low oxygen, high duckweed cover, or you tend to have very little duckweed cover and higher oxygen. There's really not a lot of, there aren't really many ponds with kind of a middle amount of duckweed cover. We also know that sediment oxygen demand just from decomposition of organic matter is really high in these systems, so that's tending to drive oxygen down as well. But what I've been really interested in is kind of this physical mixing and oxygenation process. It's kind of understudied in these smaller water bodies, definitely studied in lakes, but maybe less well understood in these small water bodies. And so that physical mixing can occur from convective currents, from surface cooling, runoff inputs that can kind of mix up or entrain oxygen, or wind. How important is wind for these small water bodies, especially relative to these other processes? Because sometimes we have ponds that look like this one on the right. There's no tree cover on it. There's no houses anywhere near it. This pond is really open. Wind is probably much more important for this pond than, say, the one on the left, which is small, tree covered. And how do we quantify that? How do we turn that into something that we could use? So I think this is the only slide with equations on it. So this is how I approached this. We know that wind sheltering is going to be a function of both pond size and the height of the landscape around the pond. So if we just pretend the pond is a perfect circle, and we say the diameter of that circle is the fetch, and then we also need to quantify the height of the landscape around it. So that's going to include the topographic height, the land surface, plus whatever's built or growing on top of it, the trees and buildings. So we normalize that fetch by the height of the landscape around it, just take an average in a 50-meter buffer, and we get this normalized fetch. Basically, the lower this number, the more entrenched or wind sheltered that site is, the bigger that number, the more open it is. So how do we get this parameter? It comes from LiDAR data, which is a fascinating resource if you've never poked around at it. There's been a recent LiDAR collection in the state over the last 2-3 years. I won't go over the details here. I wanted to put together a poster on this, but if you have questions about how this process works, I'd be happy to talk more about that. But basically, we take those raw point clouds and turn it into information on canopy height at very fine resolution, as well as the topography. So normalized fetch looks something like this. The top plot is just the landscape height. That's the blue dots, kind of arranged from from lowest to highest across the 300 ponds that are in this data set. The orange dots are just the topographic height, so just the ground surface elevation around the ponds. And you can see it varies quite a bit across sites. That's good if we're looking for an informative parameter. How this translates into that normalized fetch parameter is on the bottom. So the lower landscape height sites tend to have, they're more open, and then the more sheltered sites are on the right. But what does this look like? So here's the Alameda Pond that I talked about earlier. It actually has the highest landscape height just about in our distribution. It's one of our most sheltered sites, even though it's a 3-acre pond. It's just, that's how big the bluffs are and the trees are around the pond. Contrast this with that other pond I showed in the picture. This is out in Woodbury. This one has very low landscape height. It's very open, so it has a much higher value of that normalized fetch. And then another pond that, if I have time, I'll talk about at the end. Here, this is a Canterbury Oaks Pond in Bloomington, which had a tree removal. But as you can see, it's clear down here in the most sheltered, lowest fetch sites that we have. So how well did we do with this parameter? So this plot is just showing the observed wind speed on the pond relative to the airport. That's the vertical axis, and then that normalized fetch is on the x-axis. So the more sheltered sites are on the left, lower wind speeds, and then the more open sites are on the right, higher wind speeds. So this suggests that at least this fetch parameter is doing a good job of capturing that wind environment on the ponds. And this translates into a greater mixed depth. So we could use our continuous temperature data to figure out how deeply the ponds are mixing each day. And what this plot is showing is that as the sites are more open, they're mixing to a deeper depth on average each day. So that suggests that the wind is important for at least some of these sites. And then this is just the DO versus mixed depth. So does it matter that we can compute the mixed depth? Yeah, maybe. So the ponds that are mixing to a deeper depth do tend to have higher DO, but there's a lot of scatter here that suggests there's some other processes going on. And that process is duckweed. I think you will hear a little bit more about this tomorrow when Jacques Finlay talks about vegetation. But this plot is now showing the mean water column DO versus fetch. And you see that the more open sites tend to have higher oxygen but that pattern seems to only hold for the duckweed covered sites. Those are the dark green dots. The light green are the low duckweed covered sites, and that fetch doesn't really seem to matter for those sites. So the high oxygen there is probably due to some other processes. We're still kind of figuring out what all this means. This is sort of, we're at the cutting edge of what we're working on here. So this is duckweed cover versus fetch. So this is thinking about what sort of wind environment supports duckweed growth. Because we know duckweed's really important for oxygen and phosphorus, but it's also going to be impacted by wind. Too big of a pond or too much wind and the duckweed gets pushed around. And so that's kind of in the top left corner here, that's sort of the densest duckweed cover and a normalized fetch of maybe less than 30, a value of 30 or less. So this suggests that we could maybe use this fetch parameter to figure out whether a pond is likely to have dense duckweed cover or not. And so there's some implications there for management. So if you're going to do a tree removal, let's say, in Bloomington, Jack Distel is here, I saw him somewhere. He could talk about this, the motivations for this, but they removed the tree cover around this pond that we were already monitoring, so we continued to do the monitoring the next year. And you can see the mean wind speed almost doubled just with that removal of tree cover, which is encouraging, but we didn't really see an improvement in water quality. You can still see the duckweed growing on the pond there. And one reason for that is if we go back to our normalized fetch plot here, the green square is where it started. The white triangle is as far as it could possibly go. Like I don't actually know what the tree cover looks like, but if we were to remove all the trees and buildings around the pond, it would be at that white triangle. So that's kind of the upper limit of where you could get just with a sheltering reduction. And basically that keeps it in that high duckweed cover state. Not that it couldn't one day be one of these ponds on the low end, with low duckweed cover, but it's going to require probably some other management to get it there. So that's all I have. I had some concluding thoughts here, but I think what I'm going to do is just turn it over to Bill. I just want to make sure. Yeah, but you're going to hear so much more about the implications of some of these results in the upcoming talks. So thanks.
We will be taking questions at the end. I don't know about you, but what I learned from that is we need more water skiers and ponds to push away the duckweed. That's what I've learned. Our next talker is Bill Erb, also a research associate at the University of Minnesota Saffel, and he'll be talking about modeling pond inputs and internal processes.
Let's see. Almost there. But if you, this is yours? Yeah. Yep. Oh, yeah. Thanks.
Okay. So I'm going to be talking about some of the same things that Ben talked about, but I'm talking about it from the perspective of somebody that's been doing computer modeling of stormwater ponds rather than taking a lot of field measurements. I'll start with a little bit of background. We've actually had two projects that were quite focused on putting together models for ponds. In the phase 1 project, we were using a 2-dimensional model called SQL W2. It worked, but we found it a bit cumbersome to work with, and we decided that switching to a simpler 1-dimensional model would allow us to get more simulations done and do some of our own customization of the model. So phase 2 is really the part of it that I've been working on, and that was funded by the local road research board. So this is a schematic of what what some of the processes are that we include in this 1-dimensional model. It's 1-dimensional in that we are simulating vertical profiles of temperature and dissolved oxygen and phosphorus and chloride in some cases. So we're assuming that the pond is laterally well mixed. And I will get into detail, a little more detail on some of these processes. But before I do that, I wanted to talk a little bit about how I went about getting inputs to the model, because the model needs the hydraulic inputs, the flow rates, it needs concentrations of phosphorus and sediment and so forth. So how do we get at that? So if you have a pond model, one way to get at generating inputs to it is to use a runoff model. And in some cases, you might have a runoff model in hand already for the project that you're working on. In our case, we didn't really have effort costed into the project to put together a watershed model for each pond that we wanted to simulate. So I'm not going to be talking about watershed models in this talk. I'll talk about what I did instead. But certainly, if you have a P8 model or a SWIM model, that is a pretty good way of generating inputs. You can also use, if you have pond inflow monitoring data, that's kind of ideal. If you have an ISCO sampler at the inlet measuring water quality and some way of measuring flow rates coming in, that's a really good, a nice data set for doing a pond model. You can also do a lot with just in-pond monitoring data, and I'll talk about that a bit more in a second here. I also, in this project, made use of a big regional stormwater monitoring database that Jock Finley and Ben Janke and others put together, and I'll show a little bit about that too. So for measuring inflows to a pond, you can do it kind of directly with, say, a weir with a level sensor. There's a photo of a V-notch weir on the right of the slide here. It's one we put together for actually a chloride monitoring project. And it was really easy to put in, right, Ben? Another option are these area velocity probes. They're a bit easier to install, but I think in both cases, some ponds might be easier than others to put in equipment like this. You may not have a good access point for measuring flow. So what I'd like to do is talk about how we can use pond level monitoring to kind of back calculate what the inflow to the pond is. And like Ben, I have one slide with equations on it. Basically, we can do a water balance on the pond and say that the rate of change of storage in the pond is equal to the inflow minus the outflow. Now, we don't know what the inflow is. That's what we're trying to get at. But if we have water level data that we took using a pressure sensor or an ultrasonic measurement, and if we know what the pond bathymetry is, then we can calculate what the change in storage is at any given time. And then if we have that same water level data, and if we know what the rating curve of the pond is, as a function of water level, we can estimate the outflow. So if we then take this estimated change in storage and add the outflow, that is now our inflow. And that I have found actually works pretty well. And it's relatively easy to monitor pond level. So another nice thing about having pond level data is that you can get at what the pond is doing between storm events. And Ben in his talked about how important it is to think about how much storage is available in the pond prior to a storm event. And if there's more storage available, you probably will get less phosphorus export. So if you look at water level data between storms in a pond, and if you have an estimate of what the evaporation rate should be, you can kind of look at it and see, okay, I think we've got a little groundwater flux going out of the pond, or maybe even some groundwater flux coming into the pond. And I threw a graph in this slide showing some simulation results from the pond model that shows, so the x-axis here is the groundwater inflow or outflow rate, where positive numbers are a net inflow to the pond, negative numbers are a net outflow from the pond, and I put a line in where we think Alameda Pond is at with a moderate groundwater outflow. So you can see the lines show a pretty strong trend of increasing phosphorus export as the net groundwater flow increases. So this water balance method can be used to calculate pond inflows for years where you have water level monitoring data. But when I was going through this project, I really wanted to generate longer time series of inflows, like for 10 years, for example, and we didn't necessarily have that much pond level data. So what I did is I created a relationship between pond inflow and precipitation that was very specific to each pond. And basically, for the years where I did have some inflow data, I would also get the precipitation data for that year and set up a little regression between inflow and precipitation. Typically, the inflow for a particular hour would be proportional to the precipitation for that hour plus the precipitation for the previous hour plus maybe some precipitation from the hour before that. So a simple regression like this, and you can see in the graph where I'm plotting the estimated flow versus the actual inflow. It's not a perfect relationship, but it's good enough to give me a time series of inflow that I think is representative for that pond. And we're not always looking for exact numbers. Representative numbers can be quite adequate in many cases. So we also need inflow concentrations of phosphorus and other substances. And like I said, if you are able to put an ISCO sampler in or whatever and measure the actual concentrations, that is ideal. In my case, again, I wanted to generate kind of a long time series of inflows to these pond models. And so what I did is I mined into the big stormwater database that, as I mentioned, Jock Finley and Ben and others put together, and picked out some of the data points for kind of intermediate size catchments that I think represented the stormwater ponds pretty well. And I just started looking for relationships between measured concentrations and, in this case, precipitation parameters. So what I found is that the concentration of total phosphorus in the stormwater increased significantly in cases where there was a lot of dry weather prior to the storm event. So it's basically the old wash-off principle that if the landscape has more time to build up pollutants over time, then when a storm comes along, there's more to wash off and you get a higher concentration. So again, this is a way of generating some representative inputs for the pond model. And you can do this, once you have this relationship, you can do it for any year where you have precipitation data. Okay, that's, I think, enough about inputs. I'll talk about the in-pond processes that we were modeling a bit now. first of all is heat transfer and stratification. So that's modeling the temperature in the pond, the temperature profile in the pond, and then wind mixing when that is for the less sheltered ponds. There's light attenuation in the water column from algae and other substances that is taken into account. And then we do include some sediment heat transfer because that's kind of acts like a heat sink that moderates the pond temperatures a bit. Dissolved oxygen is important for what we're doing, and the lake model that I used to create the pond model had dissolved oxygen in it mainly to look at fish habitat. And we're not maybe so concerned about fish habitat in a stormwater pond, although based on Todd's talk, maybe I should change my mind about that. But for stormwater ponds, what we really want is to get a handle on the dissolved oxygens so we can see what parts of the sediment are anoxic and which parts are oxic and what the phosphorus release rates are going to be. Unfortunately, to model dissolved oxygen, you really need to have algae in there, and other plants perhaps. So the model gets a bit complicated to model algae growth and respiration and settling and decay and so forth. But it's possible to do, and there's quite a bit of experience in the lake modeling community on how to do that. And then finally phosphorus, which is what we're really trying to get at. Again, we have phosphorus inputs coming in from the watershed in different forms, dissolved, particulate, organic, etc. And again, the algae are an important part of the phosphorus. What? Go away. Sorry, I'm getting a little pop-up here. Okay. So in modeling phosphorus in the pond, again the algae are an important part of the system where the algae uptake phosphorus as they grow. They settle down to the bottom after they die, and so in fact algae growth and senescence is a mechanism by which a pond could potentially convert dissolved phosphorus into particulate phosphorus. But unfortunately, the algae don't really hang on to the phosphorus that long. After they die, they start decaying and the phosphorus is released right back. So, let's see. Okay, so these processes that I've outlined in our pond model would be appropriate for modeling an algae-dominated pond like Camden Central, shown in the left image. But as Ben indicated, a lot of ponds around the metro area actually have a lot of duckweed on them. And so we thought it would be appropriate in this project to add the effects of duckweed to the pond model. And it's a pretty unique part of the study, I think. So I did a lot of literature searching to see what information is available on duckweed, and there is some. And what we learned is this, that first of all, having this layer of duckweed actually increases the surface albedo, so more light is reflected off the surface than would be if there was no duckweed there. So that would tend to cool off the pond a bit, which is probably just fine. But of the light that doesn't reflect, a lot of it gets absorbed right near the surface of the pond because you've got this thick layer of plants that's absorbing light. And what that does is it tends to create a stratification in the pond where there's a warm surface layer and then it's cooler beneath the duckweed, and we've measured that in the field. Maybe the most important effect of the duckweed is that it reduces surface aeration of oxygen. So it acts as a block to oxygen transferring from the atmosphere down into the pond. And that's it's not something we've measured in particular, but there's some data in literature on this. And on top of that, it seems that when the duckweed photosynthesizes, it's not putting that oxygen into the water, it's releasing it to the atmosphere. So that's a kind of another loss of oxygen supply to the pond if it is covered with duckweed. So the first 4 bullet points, these are all processes where there was at least a little bit of information available in literature, and so I had some numbers to put into the pond model. I suspect that the duckweed probably changes the evaporation rate from the pond in addition, and I suspect that having this layer of duckweed probably reduces wind mixing if there is some wind on the pond, and there's really not much information available on that, so I didn't really try and incorporate those processes into the pond model. But in any case, we did get a model component added for duckweed. We were able to simulate the observed biomass in ponds reasonably well. And actually, if you look at the plot on the right there, this is kind of demonstrating a competition between duckweed and algae, where the duckweed, which is in the blue line, has a higher biomass earlier in the year, and then it dies off a bit, and then the algae concentration, which is in red, kind of takes over later in the year. It's kind of a random result, but the pond model can actually capture some of the competition for light and nutrients between algae and duckweed. So the duckweed model worked reasonably well, but we didn't get to the point where we could, for example, reproduce year-to-year variations in duckweed biomass. We did have some measurements of that, and the model didn't seem to quite capture interannual variations